Illustration of Prim's algorithm. In the last lecture, we learnt about Prim's algorithm, which is a greedy algorithm for finding minimum spanning tree of a weighted, connected and undirected graph. In this lecture, what we are going to do is we'll take a graph and then we'll see how to construct the minimum spanning tree of this graph using Prim's algorithm. So whatever we learned in the last lecture, that was the process of how to convert it using Prim's algorithm. And here we are going to practically see how we can convert a graph to its corresponding minimum spanning tree. Let us start with this. What we'll do, we'll take a graph and then we'll follow the steps that we learned in last discussion. Let us say your graph has these vertices A, B, C, D, E and F. I'll name these vertices. Vertex A, B, C, D, E and F. Let us have some edges here. What I'll do is, whatever graph we took during Kruskal's algorithm lecture, we'll take the same graph so that you'll have a clarity on what is the difference in each step when we do using Kruskal's algorithm and when we do using Prim's algorithm. So you have an edge AC here, then you have DE, EF, DF, and then you had an edge CD, CE, and then BD. This is the graph that we used when we were learning Kruskal's algorithm. So with the same thing, we'll do Prim's algorithm. And the edge weights were 5, 3, 1, 2, 2, 4, 3 and 1. With this graph, let us see how to apply Prim's algorithm. So the first step is to identify an arbitrary vertex from which you want to start building minimum spanning tree. In case of Kruskal's algorithm, you had to specifically choose the minimum weighted edge so as to start with the algorithm. But in case of Prim's, we learned that you don't have to use any specific vertex. You can choose any arbitrary vertex, and the reason is that coming to edges, you have to choose the minimum weighted edge because a random edge may or may not be part of the MST. So you can't say that any edge can be chosen at the starting of this. But coming to vertex, all the vertices will anyway be part of the MST. Because of that, you can start from any arbitrary vertex. So we'll start with, let us say, vertex A. If vertex A is my starting point, what is the rule in Prim's algorithm? At every point, I have to find the smallest edge that is passing from the set of vertices which are already in MST to the set of vertices which are not in MST at this point. This is what you do in every single step of Prim's algorithm. At this point, we'll consider that whichever vertex you have already chosen, that is here it is vertex A. Vertex A is already part of MST and all other vertices, they are as of now outside the MST. In each step, you will be taking one vertex to the set of MST vertices. So as of now, you see A is part of MST and all other vertices, these are all outside the MST. What is the next step? You want to identify whichever is the smallest edge that is passing from the set of vertices inside MST to the set of vertices outside MST. So here if you see, from A, which is the smallest edge that is going out, it is this edge AC, which is having an edge weight of 3. So let us draw this edge AC. I am adding AC into minimum spanning tree. AC is added, which is having edge weight of 3. So at this point, I have two vertices inside the MST, A and C, and all other vertices, these are all outside the MST. What is the next step? I have to find the next smallest edge which is passing from the set of vertices inside MST to the set of vertices outside MST. So from A or C, whichever is the smallest edge that is going out. So which is that edge? That edge is CD here. If you see, CD is having an edge weight of 1, and that is the smallest edge which is passing from the set of vertices inside MST to the set of vertices outside MST. So I'll draw vertex D here. This is vertex D, and CD is of length 1. This is my present MST. So you can see that at every point when we are developing Prim's algorithm, your MST is always connected. But in case of Kruskal's, when you were building the MST, you had many disconnected parts. And it so happened that at the end of your algorithm, it will be a single connected component. But when you are building the algorithm, at that point in Kruskal's, you had many small components. But in case of Prim's, you will always have a single connected component. Let us see what is the next step. So as of now, A, C and D, these vertices are already part of our MST. E, F and B, these are the three vertices that you have to add to the MST. What will you do? You'll see which is the smallest edge that is passing from the set of vertices inside MST to the set of vertices outside the MST. Which is that smallest one? You have two options here. One is edge CE and the other one is edge DE. Both of these are having edge weight of 2. And let us say we are choosing CE. So in this case, you want vertex E here, vertex E, and I'm adding edge CE. CE is of edge weight 2. So at this point, I have also added vertex E into the set of MST vertices. So at this point, I have 4 vertices as part of MST. What is the next step? The next step is to identify the smallest edge which is passing from the set of vertices inside MST to the set of vertices outside MST. Which is that edge now? You can see EF is passing from E to F. E is already part of MST and F is not part of MST, which means EF is the smallest one. I'll pick EF. So F is the vertex here and EF is of edge weight 1. At this point, there is only one more vertex which is not part of MST, which is B. What will I do? I'll see whichever is the edge which is going to be and is the smallest. Which is that edge? It is BD. BD is of edge weight 4. If I put B here, BD is of edge weight 4. Why did I not choose AB? Because AB is of edge weight 5, which is larger than BD. At this point, if you see, all the vertices of this graph are already part of this MST. If you have V vertices, you should have V minus 1 edges in order to connect. Here if you see, you are having 6 vertices, and in order to connect these 6 vertices, you have 6 minus 1, that is 5 edges. So at this point, you can say your Prim's algorithm is complete. So this is how you can convert a graph into its MST using Prim's algorithm.